Well, hello again, class. It's time for the companion lecture with the ANOVA lecture for MCPs here. So, multiple comparison procedures. As I pointed out last time, if the ANOVA F rejects the null hypothesis, so if your obtained F value, the mean square between divided by mean square within, if that number is high enough above 1, your obtained F will be greater than your critical F, therefore rejecting your null hypothesis. It favors your alternative, but it doesn't clearly support your alternative hypothesis usually, because your alternative hypothesis is not just going to be that there's some difference somewhere. That's all the F tells you. Okay, the alternative here for the basic ANOVA F has to be there's any difference anywhere. Okay, it doesn't tell you which groups have different means. It says there's some difference somewhere. This fact, along with the lack of robustness to unequal variances, which I haven't really mentioned before, but it's a good point to remember about one-way ANOVA. It makes us not really rely completely on the ANOVA F as the most important statistic for a one-way design. It's where you have to start is to get what's called the omnibus F, or the across all groups F value. It's a starting point. It tells you, is there a difference anywhere? Okay, great. Now what's the next step? Well, we need tests for the multiple differences that exist between the J means. For example, which of the groups is best at detecting liars? And this would be certainly an interesting study to run. Secret Service agents versus judges versus psychiatrists. The significant F value here would merely say that there is a difference somewhere among those three groups, but you don't know where it is. But to find that out, you need to run a multiple comparison procedure to test out the pairwise comparisons. So a pairwise comparison is a difference in means, okay, between two means at a time. If you have J means, so the example I gave you has three groups, so you would have a C equals J times J minus 1 divided by 2 equal, C here is the number of pairwise comparisons, so in this case it would be 3 times 3 minus 2, which is 2, so 3 times 2 is 6, divided by 2 is 3. So in this case it just so happens that there are the same number of groups as there are comparisons, 3 each, but that doesn't always hold up. So if you have 6 groups, then it would be J of 6 times J minus 1 is 5, 6 times 5 is 30, divided by 2 is 15. Okay, 15 comparisons if you have 6 groups. There are 6 comparisons if you have 4 groups. Okay, so you just need to be able to run this formula pretty quickly to decide how many pairwise comparisons you have. Now, that's assuming that you want to actually conduct all pairwise comparisons. You don't always want to do that. If I'm curious as to what treatment might work best, and I'm comparing, a 10 milligram group versus 20, 30, 40, 50, all the way up to, let's say, 200 milligrams, I might not be interested in comparing each and every one of those differences, 20 milligrams versus 30 milligrams, 10 milligrams versus 30 milligrams, and so forth. That would be just tons and tons of multiple comparisons that I might not be interested in all of them. Maybe I want to kind of just jump to 10 milligrams versus 100 milligrams. Is there a difference there? Okay, great. Then I'll go with the 100 milligram group. Okay, maybe there's not a difference between 100 milligram and 200 milligram, so I'll just go with 100 milligrams. That's good enough. Okay, so it all comes down to your hypotheses. Which groups do you really care about, as in terms of which are different, which are greater than others or less than others on whatever measure you have. Okay. So you have a hypothesis for each pairwise comparison, and that is, as usual, the null hypothesis is that there's no difference between the mean of group J and the mean of group J prime. Okay, just two different groups that you have within your overall study. Your alternative is that there indeed is a difference between those two groups, okay? And you can frame that in terms of a direction, that this group will be higher than this group, or this group will be lower than that group. Doesn't matter. Anything other than there's no difference is an alternative hypothesis, okay? So, okay, what about error rates? Now this comes back to that point I mentioned during the last lecture as to why you need multiple comparison procedures, why you can't just run a series of t-tests whenever you have multiple groups. You can't do that because the t-test does not control for type 1 error across multiple comparisons. The t-test would just set alpha at 0.05 for each and every one of those comparisons, and this formula here shows you why that's a problem. So what is the probability of at least one type 1 error? You want that to be a low number here because, again, a type 1 error is an incorrect rejection. It's rejecting the null when in fact the null is true. Okay, there's no difference between your groups, but your statistic could be telling you that there is a difference. You're likely to get that error if you just run a bunch of t-tests. It's very powerful, but it's not good. It leads to too many type 1 errors, okay? So, again, C is the number of pairwise comparisons here. This is the formula you need to conduct here. You're not going to have to do this yourself. I just want to present that to you. What you're doing is you're setting alpha prime here. This is the alpha that you set for each comparison when you have multiple comparisons. So alpha by itself is typically 0.05, but if you have multiple comparisons, you don't want alpha at 0.05 for each and every comparison. It'll add up too much. So error rate per comparison sets alpha prime to 0.05 for each comparison. If you do that, so that's the same thing as running just a bunch of t-tests where you have alpha 0.05 for each and every one, then you run the formula here. If you have three groups here and 3 pairwise comparisons also, you get the probability of at least one type 1 error is basically 14% here. So that's pretty high. If you run several experiments trying to figure out if you have a treatment that works better than some other treatments, well, 14% of the time you're going to get a false reading. You're going to get 14% of the time it's going to tell you that this treatment is better than the other ones. Okay, but that is actually not going to be the true 14% of the time. 14% of the time it's just going to be, hey, there really is no difference, but your study is telling you that there is a difference. That's problematic. Okay, to fix that, you need a multiple comparison procedure, and one way that it can control this is by utilizing error rate, what's called family-wise, utilizing the family of pairwise comparisons that you have rather than per comparison. Okay, per family rather than per comparison. Error rate family-wise controls the probability of type 1 error, of at least one type 1 error, at a maximum of 0.05. So it does not let you get above alpha of 0.05 no matter how many pairwise comparisons you have. That is a very strong way of controlling for a type 1 error. So it holds alpha at 0.05 for a group of C comparisons by keeping alpha prime small. So alpha prime in this case is not going to be 0.05. It's going to be less than 0.05. So to give you an example here, for the liar study, okay, Secret Service versus judges versus psychiatrists, you have 3 groups. C, you run the formula, it just happens to be that the number of comparisons is also 3 here. 3 pairwise comparisons, Secret Service versus judges, Secret Service versus psychiatrists, and judges versus psychiatrists. So the error rate per comparison is just 0.05. As I pointed out, if you just did a bunch of t-tests, which is very improper, then you would have too high of a probability of at least one type 1 error. However, if you control error rate family-wise, which is a much better thing to do, then you find that basically this is 0.05 divided by 3, okay, which is C, the number of comparisons that you have. 0.05 divided by 3 is basically 0.17. So that means that when you're looking at your p-value, okay, so you run a multiple comparison procedure, you compare Secret Service versus judges, okay, and you find, let's say you find p of 0.04. Well, normally you'd be happy because you'd say, hey, I thought that Secret Service would be better than judges, and sure enough, the mean for Secret Service is higher than the mean for judges at p of 0.04. You're used to comparing it to an alpha of 0.05, but in this case, that's not accurate. You need a p-value that's less than this, that's less than 0.17 basically for each one of these comparisons, assuming you have a hypothesis for each one. That's what you need to do, okay? So it's more conservative here, in other words. You can't just have a p of 0.04 or 0.03 or even 0.02. You really need to have a p of like 0.01 or less in order to be less than 0.017. Okay, and that's how this works here. It makes your tests more conservative. It requires a lower p-value based on lower alpha prime levels. Okay, So what if you have an additional group here? So j equals 4. So you run the numbers. The number of comparisons is 6 here, as follows. Okay, all the possible pairwise comparisons for 4 groups. Error rate per comparison, if it's 0.05, then all of a sudden your probability of at least one type 1 error is 26.5%. Okay, so every 1 out of every 4 times you run this study, you're going to get a false reading here where it's telling you that you got a difference somewhere and there really isn't that difference. Okay, that's a big problem. So you want to control error rate family-wise, setting alpha prime at basically 0.05 divided by the number of comparisons. You have 6, which gives you basically 0.008. Okay, so that's what the Tukey, that's one of the more popular MCPs, although there are several. Refer to chapter 10 in your book for more information on a few different MCPs that are out there. The Tukey MCP, that's what it does. It automatically controls the probability of at least type 1 error family-wise. Okay. My favorite MCP is called the Bonferroni, which also controls family-wise, but there are pros and cons with each one, but I prefer the Bonferroni because it's very conservative. It basically just, it takes alpha of 0.05 and it divides by the number of comparisons that you have, okay? And it nicely controls for the type 1 error rate in that way, okay? But again, chapter 10 in your textbook gets into greater detail as to which MCP you might want depending upon aspects of your data. Okay, there are some that are better than others if you can't assume equal variances. Okay, the Games Howell MCP is appropriate if that assumption of equal variances is violated. But normally the Tukey or the Bonferroni, normally those are going to be perfectly fine. Okay, but here is more about the Tukey. That's really the only one I'm going to highlight in this lecture. We'll use a t statistic for multiple comparisons and what's called the studentized range distribution that has a critical value of q divided by square root of 2. Just providing that for your information, just an FYI on this slide, just so you can kind of see where this stuff is coming from based on a different distribution here. So it's not a t distribution, it's not an f distribution. We have those tables at the back of your textbook. This one is not at the back of your textbook, although it's at the back of some statistics textbooks where you can see it's sometimes called a Q table or a studentized table. So you're not going to have to worry about looking this stuff up, but I've gotten you used to writing out and thinking about these various rows, so that's what I want to do here for this MCP, because it's treated in a similar fashion as the other test statistics that we've had, Z, T, F, you'll see chi-square. This is a different one, Tukey's MCP. So what is the situation or hypotheses here? Well, you have at least 2 independent samples. Okay, it's assuming independence. Typical null hypothesis here that you have no difference between 2 of your groups. An interesting point with Tukey is that you're interested in all pairwise comparisons. I pointed out before that you might not have a hypothesis about all your pairwise comparisons. And so if that's the case, if you don't have a hypothesis for all of your pairwise comparisons, then you might not want to use Tukey. But Tukey is kind of a fallback if you are just going to look at all your pairwise comparisons. You're just kind of looking for differences. Okay. It also assumes that you have equal n's. Okay, it's an important point to remember. Your test statistic is as follows here: the difference in your means of your 2 groups divided by square root of 2 times your mean square within from your F ratio divided by n. Okay, the Q divided by square root of 2 distribution is what it is, and you need, if you were to have this table look up critical Q values, and you would need J and degrees of freedom within and alpha 0.05, but again, you're not going to have to worry about that. And there are always assumptions built in here, such as normal populations, bell curves, equal variances between your 2 groups, and independent observations. Okay, so as my final slide here, just want to run some numbers here so you can get an idea of how this looks based on that formula I just gave you for so it's not the t distribution here. This is t for, it's similar to the t, but this is for the Tukey MCP here. So the formula is different from your t formula. Tukey's MCP gives you 3 stats, just inputting some numbers here so you can see Secret Service versus judges. You get a critical Tukey T of 2.42. For Secret Service versus psychiatrists, it's 2.05. For psychiatrists versus judges, it's 0.37. Okay, so these are observed T's, not critical T's. The critical T you would look up based on the studentized or Q table that you don't have access to. You would input these numbers just so you can work with the table, and you would get this critical Q value or T value, whatever. It's what you're comparing these observed T's to. So 2.4, you have to have a difference between groups greater than 2.4 in order to say, hey, it's a significant difference. That one is, and the other ones are not. Okay, and that one barely is. So you find that only the Secret Service agents versus judges, that's the only one that's different. You'd have to look at the means to see which group did better, Secret Service versus judges. Okay, I'm not showing you those means here. Oh, I'm sorry, I am. Okay, 64. 64 is the mean for Secret Service, 56.57 for judges. So here this shows you that indeed your Secret Service agents are doing better at detecting liars than your judges are. Okay, that's the only significant difference here. Secret Service not different from psychiatrists, psychiatrists not different from judges. Okay, and that's that's basically how you would write up your results as well. You would have to specify where are the differences and where aren't. Where are there equivalents between groups as well. Okay, so that was a brief primer on multiple comparison procedures, the Tukey in particular. I just need you to be aware of these, be aware of why you need multiple comparison procedures instead of just running a bunch of t-tests. That is of primary importance. The key issue is controlling for the increase in type 1 error rate when you have multiple comparisons. Okay, multiple comparison procedures in one of the many things nice that they do is, the Tukey, for example, or the Bonferroni, they're conservative. They prevent researchers from just kind of throwing a bunch of stuff at the wall and seeing what sticks. You can have studies that involve just a ton of comparisons. Let's say you see a correlation table and it's presenting, dozens of potential correlations. Well, always be on the lookout for this. Always be on the lookout for a presentation of a giant correlation table or anything where you see a bunch of comparisons among groups. Always be on the lookout for, well, what's their alpha level? Are they just pointing out which ones are less than 0.05? That's a problem because they're not controlling for type 1 error rate. You can't just use 0.05 for all of your comparisons like a big fishing expedition to see, which ones end up being less than 0.05, because what can happen there is, you might find a few that are less than 0.05, but because you're not controlling for the increase in type 1 error rate, those could be type 1 errors. Those could be just by chance they happen to be less than 0.05 because you have so many comparisons. By chance, it's likely that some of them are just going to be below 0.05, and it's not going to be anything meaningful. Okay, so MCPs control for type 1 error by just enforcing, kind of forcing researchers to not accidentally say that, wow, look at that, there's a difference there, when in fact there might not be. Okay. Okay, so that concludes the lecture on MCPs. We're getting towards the end of this course. Next lecture, and I believe your final lecture, is on correlation and regression. I look forward to diving into that next.